How's it going, ladies and gentlemen? Mr. Donnie here, taking a look at 14.5, temperature and rate. Why does reaction rate increase as temperature goes up? Well, reaction is all about things colliding with other things and then reacting. So it has a lot to do with pretty much that. So why does the reaction rate increase as temperature goes up? Well, let's think. If temperature goes up, these things are moving faster, which means they're going to have more energy, which means they're going to collide harder, and they're also going to collide more often. So reactant molecules collide less often. False. They're going to collide more often. Reactant molecules collide more frequently with less energy. So close. Reactant molecules collide more often and with more energy. Yeah, ding, ding, ding. All right, but let's read all the choices. Reactants collide less frequently. That's wrong. And the activation energy is lower. That is also incorrect. Activation energy stays the same. It's just things got more energy. 25. In the energy profile of a reaction, the thing that exists at the top of the curve is called the blank. So why don't I draw one of those things? So let me draw an exothermic reaction. So the thing that's at the top right here, we call the activated complex. That would be A. Right? I'm going to call that AC. Remember, where you start is the heat of reactants. Where you end up is the heat of products. The change between those two is the delta H for the reaction. The amount of energy that it takes to get from your reactants up to your activated complex is your activation energy. And I think that's all the big stuff that we talked about. Cool. 26. What is the activation energy for the forward reaction below? Well, for the forward reaction, we're going this way. We're going left to right. We start here, and we got to get up to here. So A would be our activation energy for the forward reaction. 27 says, what is the activation energy for the reverse reaction? Well, reverse means we're starting with the products here, and we're going to go backwards to our reactants. So we have to start at the bottom and make it all the way to here. All right, so that is both A and B. Those combined would be the activation energy for the reverse reaction. All right, so here we got the Arrhenius equation, which you need to be familiar with. So K is that reaction constant. E is that number. And then we got EA, which is the activation energy. R, which is usually this is what we end up using, joules per mole Kelvin. And T is the temperature in Kelvin. So what is this A? A is the collision factor. Right. So we know that temperature affects the speed of a reaction. We know that activation energy will affect it too, but then we also have to account for how the things must collide in order to react, and that's A. That's how we factor that in. So the first order reaction has a rate constant of this number at that temperature. What is the magnitude of K? So it's looking for a new K at a different temperature if that is our activation energy. All right, so things we know. We know K1, we know K2, or it wants K2, and we know activation energy. So hopefully we know of an equation that links all these things together. All right, so should have come across this equation at some point. ln of K1 over K2 should equal the activation energy over R, and then in parentheses 1 over T2 minus 1 over T1. Alright, so let's assign the K that they gave us as K1. So now we got to solve for K2. Right? We know EA, we know the temperatures, R is a constant. Thing to look out for though is when you go to use your R, it's 8.314 joules per mole Kelvin. And the activation energy that they gave us is in kilojoules. So we got to convert that to joules. We got to make sure our units are in agreement. So that would be 44,500 joules. That'll be what gets plugged in there. But before we deal with a bunch of ugly numbers, let's deal with simple letters. So first off, I got to get rid of this natural log so I can get access to that K2. So in order to do that, you do e to the on both sides. The ln cancels out on the left side, and you get e to the EA over R times 1 over T2 minus 1 over T1 in parentheses. So now we got to get K2 by itself. Well, there's a couple of ways you can do this. It's on the bottom here. All right. You know what? It's just algebra. You guys can figure that out, right? So you get K2 equals K1 all over the e to the EA on R times 1 over T2 minus 1 over T1. Right? So now it's just plug and chug. We know K1, we know EA, we know R. T2, T1 is just solve. So K2 equals 2770. That's what I got. I think that's it. Yep, that's it. So it's just a lot of algebra, right? It's not crazy. It's only a couple of steps. It's just algebra. So see you in class. Bring questions.